Hello. If you have dealt with the exponential growth and exponential decay models, you're aware that if we have a differential equation that describes our model, then in order to solve it, we need to integrate it. That integration can become quite tricky when it comes to more complicated models, especially with nonlinear functions. However, I will demonstrate how we can use MATLAB and particularly the symbolic toolbox in order to solve differential equations and to be able to use the result and display it as functions, just as we have done with the exponential growth. Now we want to set up our model as a differential equation. Then we're going to solve or integrate that differential equation symbolically in MATLAB to get a solution. And we'll convert that symbolic solution to an algebraic solution in order to make plots, for example, in the population model of the population as a function of time. So let's start by starting a new script, and we can call that Logistic. So it's our logistic model equation. It's actually a typo, it doesn't matter. Right, so how do we set it up? If we want to have a symbolic equation, we need to define symbolic variables. So the first thing is our equation will be y of t, where y specifies the population and says it's going to be a function of time, in parentheses t. And then we have a couple of parameters which we define symbolically as n0, the initial population number, r0, which is the growth constant, k, which is a scaling factor, and time, which is our simulation time. Okay, then we need to set up the equation. So eq, just as a variable name, and we need to specify that this is going to be a differential equation. So the differential equation, and we want to have that as y of t. And it's specified as with the logical equal, which is equal, specified as r0, the rate constant, times y. And if you remember exponential growth, this is what exponential growth looks like. Some constant times the population size. And however, in the logistic case, this is extended or expanded. So the way it's expanded is 1 minus. So 1 means that first term will just be the logistic growth, and the second term will depend on y to make sure that if the population gets large, there's something that slows it down again. And what we're going to use is a scaling factor of k, and otherwise it's dependent on the current size of the population. So this leads to something that is an inverted parabola, and this will be our differential equation. So that model now needs to be solved, and to solve a differential equation model we need d solve of eq. So this is how we solve it, and the solution we can get it as sol for solution, right? Except there's a small caveat here. If we want to not have a generic integration constant but a specific interpreted constant, then we need to specify the starting value for y0. And we can do that in single quotes by saying y at time 0, which is the population at time 0, the initial population, and we can specify here as n0, just a symbolic variable, but later we can turn that into a number. And with this thing we can define the solution, and we have the solution if we execute the code. And there is a bit of a problem here, namely that we have a logarithm in that solution, and the argument of that logarithm contains a minus. So there's a nice trick here that we can use to get rid of that logarithm, and that is to just ask MATLAB to simplify the solution and rewrite it. So make a simplification of sol and write it again into the variable sol, and then we'll get a solution which looks by no means simplified, which looks even more complicated. But the good thing is it doesn't have a logarithm anymore. So this is something where we can work with without further trouble of considering positive or negative numbers. So we can now go about and use that solution to plot it, but we need to first convert it to an algebraic function. So we define a variable sol_alg and we use a MATLAB function to convert sol into the algebraic version. And to do so, we need to specify an argument called vars, which are all the variables that we're going to need later on into the equation to be able to plot it numerically. So all the variables go in a single array, which is in square brackets, and we'll have the initial population n0, we'll have the rate constant r0, we have the scaling factor k, and we have the independent variable time. So with this algebraic solution, we can now go about defining functions that will be able to plot directly. So it will be anonymous function derived from that expression. So if we specify them if we want to use different initial conditions to see how the function behaves depending on initial condition, we can just put the initial condition here and say, for a starting condition of 100, fun100 is supposed to be the anonymous function at our variable is going to be time, and then we'll use sol algebraic, the algebraic solution, but we need to now specify all the four variables, just make that a little bit nicer, that we had before in that same order. So we put the initial condition, which is the starting population of 100. Then we specify an R0 as 0.0347. We just take that from the materials. The scaling factor should be 1000 in our case, and time will just remain time. And if we have this function, we can just copy and paste it to choose another initial condition, where we need to know that the crucial thing is how does the initial population relate to that scaling factor. So specifically, it depends on whether it's smaller or larger than the scaling factor. So to pick one example of a larger initial population, we can choose 1500, and then we give it the corresponding name, which is fun 1500, to show that different initial condition. Now we have set up two functions, and we can plot both if we specify two more things. So we need to specify the limits over which we want to see them, so limits in terms of time, and we can say we want to see it from time 0 to times 300. So that should be the limit of our plot, and then we can specify that we want to have hold on, namely we want to see both functions in the same graph. And then we use fplot of fun, say fun100, using the limits. That will just be our first plot. There's one thing that we can do, we can specify the line width. Because by default MATLAB's line width is very tiny, then if we use the line width argument and say it's 3 rather than, I think the default is 0.5 or something, then the line will be thicker and better to see. And this code we can just copy, paste, and define that we want to have the plot of the second function, which is fun 1500. And that code can now be executed and gives us our plot. So here's what the plot looks like. What can we see? starting from an initial population of 100. Population rises first exponentially, then levels off and reaches a final value of around 1000, which is a steady state population that is maintained forever, according to this model. If, however, we start at 1500, the population will decay exponentially until it reaches, well, incidentally, that same level, 1000, and remain there forever. So the model predicts exponential growth or exponential decay initially, depending on the starting population, but after some time leveling off and a stable population that is independent of the choice of initial condition, and that is in that case exactly the value of the scaling factor, which is 1000.